Previously on Chemistry Z, we looked at the history of how new elements were discovered. And also, we looked at the different versions of the periodic table. This isn't even my final form. But now, we must travel to a remote mountain to study under the noble gases and find out the secret to their peaceful nature. These secrets shall be revealed in today's exciting episode of Chemistry Z. Here are the retrieval questions for this lesson. You know what to do. Elements were arranged in terms of their atomic weight. Our modern periodic table arranges elements by their atomic number. Roughly 90% of the periodic table is made up of metals. Mendeleev left gaps for undiscovered elements. We saw in the last video that he was able to predict the properties of these elements. Clickety-click the card to be teleported over to that video. Not gonna lie, this is a pretty short video because it's a short part of the curriculum. Group 0 are very modest, mild-tempered, they trouble no one. And because of that, I'm going to go over other things in this video as well, just to spice it up a little bit.
Why, man? Why?
Look at these 4 locations: a toilet, bacteria, the sun, and the ocean. A noble gas was discovered in one of these locations. Spend some time trying to guess which location of these 4 did we discover a noble gas. It was the sun.
What, we've been to the sun?
Not really. Every element has a fingerprint. But unlike our fingerprint, it is a specific wavelength of light. Remember from my video on 5G that different colors of light have a specific wavelength, which is the distance between 2 peaks or 2 troughs. And as we can see, the redder the light, the longer the wavelength. We can split white light into a spectrum. Rainbows are a good example of this. The white light coming from the sun is split when enough water droplets are in the atmosphere to create that spectrum, that rainbow. This spectrum should be continuous, which means there should be no gaps there. But what happens is that certain elements will absorb specific wavelengths of light. So the light doesn't end up in your eye because it's been absorbed by that element. Let's simplify this and have just 3 wavelengths, 3 colors of light: red, yellow, and blue. Notice that they all have different wavelengths corresponding to their position on the EM spectrum, the electromagnetic spectrum. This atom here absorbs the yellow light, so you don't see that specific wavelength because it's been absorbed by the atom. That means that if we look at this spectrum of light coming past this atom, we'll be missing a section corresponding to that yellow light. This is the fingerprint for this specific element because it absorbs that specific wavelength. Since each element has its own unique fingerprint, you don't have to be at the scene to know that an element has been there. This is just like you getting bagged by Jegz because your own fingerprint was at the crime scene. Like the feds, scientists have a database of all the elements' fingerprints, so they match it up when they see a specific missing color of light. Just like if your fingerprint is in the system, they'll be able to capture you essentially. This brings us to the absorption lines from the sun. You see bare lines here because we have different elements inside the sun, so different elements are absorbing that light, that specific wavelength. Also, some elements have more than one line. For example, line B and A are both from oxygen. Yes, there's oxygen in the sun. Scientists at the time could account for basically all of the lines apart from this line here in D 3. They concluded that a new element must be inside the sun, an element that hasn't been discovered on Earth yet. And so they named that element after the Greek god of the sun, Helios. They named it helium. The next one discovered was argon, which was super hard to isolate, so they literally named it the Greek word for lazy, argon. Then they used fractional distillation of liquid air to find the other 3 noble gases, krypton, neon, and xenon, which come from the Greek words hidden, new, and stranger respectively. One of the reasons that these elements were hard to discover was because they hardly react. Group 0 are also known as the noble gases. The secret to this unreactivity is the fact that the noble gas have 4 outer shells. So helium has 2 electrons in its outermost shell, neon has 8 electrons, and argon has 8 electrons as well. Having a full outer shell makes an atom very stable, which is why every other atom reacts to either gain or lose electrons, so they can be bad and bougie like the noble gases.
I wanna be like you. I wanna walk like you. Talk like you.
One of the trends that you need to know for noble gases is the trend in their boiling points. And it increases in a certain direction. Either up as you go up, it's either increasing as you go up the group, so from argon to helium, or when you go down the group, when you go from helium to argon. Spend some time thinking about whether you think the trend in boiling point increases as you go up or as you go down. Well, the boiling points increase as you go down the group.
It don't. It don't go down.
Robert, it goes down.
No, it don't.
It do go down.
Oh! Don't!
Would you like to know why?
No.
Well, I'm gonna tell you anyway. Notice that the atoms get larger as you move down the group. When atoms come close to each other, they experience an attractive force.
Yeah, baby, come closer.
These forces are weak intermolecular forces. The larger atoms have more intermolecular forces than the smaller atoms. If we put in enough energy to break 2 intermolecular forces, notice what's happened. Helium is now free to be a gas and move around, but neon and argon are still held together, so they're not gases yet. That's why helium has a lower boiling point than the other 2. But then we keep increasing the heat energy. Look what's happened. We remove 1 more intermolecular force. Now neon is free to be a gas, but argon is still not a gas. That's why it has a higher boiling point than neon and also helium. And then we add more energy, and now the argon is also a gas. You can summarize all of that by saying the boiling points increase down group 0 due to larger atomic size and therefore more intermolecular forces. And there we go. Lesson done.
Yeah!
I told you this was a short one. Use the timestamps if you want to skip to anywhere on the video. Grab my flashcards and revision timetable in the description below, and I'll catch you guys in a bit.